Let's now apply our definition of electric field to point charges. Let's develop the electric field for a single point charge Q. We would like to find out the electric field at some location a distance r away from this point charge. So imagine that we probe with a small little test charge which we'll call Q sub 0. And we'll assume that is positive, just like we'll assume that this point source charge is also positive. There would be a force acting on this small test charge that is equivalent to K times Q sub 0 divided by the distance between them squared. Then, if we were to calculate the magnitude of the electric field, we would use the definition we had developed earlier, which is the force per unit charge at that location. So that's the force at that location, which is equal to, by Coulomb's law, F equals K Q1 Q2 over R squared. Q represents this charge, and Q sub 0 represents the test charge. And the bottom is the charge at that location. So that's the test charge Q sub 0. And you'll notice that Q sub 0 cancels out. So the electric field does not depend on what you're probing with. The electric field strength at that particular location will be equal to KQ, that's the point charge, divided by the distance squared. If we were testing with a positive test charge and it had a force to the right, then we would know the electric field would also be to the right, because the electric field is defined as the same direction as the force on a positive test charge. Had this been a negative test charge, then the force would be acting inwards for this positive point source, and we would have a force that was in the opposite direction of the electric field. Or in general, you can remember this key idea. The electric field lines always move away from a positive point charge. If this was negative, then they would be moving towards it. So electric field lines always move away from the positive and they go towards the negative. If you have several point charges, let me show you a picture of that. So imagine you had 3 different point charges, Q1, Q2, Q3, and at this particular location you decide to place some test charge and probe to see what is the net electric field due to all 3 of these charges. Well, in this case, then you have to find the total electric field by taking the vector sum of all the individual fields at that point from all the individual charges. Essentially, the electric field at that location would be equal to vector E1 plus vector E2 plus vector E3. And of course, if this involves directions, you'll have to break it up into x and y components. Let me just show you what these directions of these electric vectors, field vectors, would point. And you'll see here I have electric field 1 pointing to the left. Why? This is a positive test charge being attracted towards this negative point charge. And so the electric field is in the direction of the force, which would be pulling it to the left. E2 is diagonally towards Q2 along this line that is between these 2 charges, the test charge and the point charge. And then E3 is actually away because this positive test charge would be repelled from this point charge and pointing it upwards here. And so what you would do is you would find each of these electric fields by using the formula E1 would be equal to KQ1, the magnitude of that, divided by R1 squared, and R1 would be this distance. Then you could do the similar thing for E2, which is KQ2 all over R sub 2 squared. R2 would be this distance. And then similarly we have also E3, which would be K times the absolute value of Q3 divided by R sub 3 squared, which would be this distance. Once you found out the magnitudes of each of these 3 electric fields, then you would, I would say, break up E2 into x and y components and add all 3 of these vectors vectorially to find your resultant electric field. Okay, I think you should be ready now to tackle on some problems involving electric fields.